Hello everyone, welcome back to Mining of Massive Datasets. We're going to continue our discussion of clustering today by looking at the k-means algorithm. Recall that we previously looked at another way of doing clustering called hierarchical agglomerative clustering. Now that algorithm worked really well in terms of producing clusters, but unfortunately it doesn't work really well for large datasets because of its computational complexity. The k-means algorithm, or the k-means family of algorithms actually, is a way of addressing that problem of creating algorithms that are computationally tractable and work with really large data sets. Now the k-means algorithm assumes a Euclidean space and a Euclidean distance. And the first step is to pick k, the number of clusters. Now, for now, let's just assume that we pick a number k and say that's the number of clusters that we finally want. Towards the end, I'll show you how to actually pick this value k. For now, let's just assume that k is a given. Now we're going to initialize our k clusters by picking 1 point per cluster. For example, we could just pick k points at random and assign 1 point to each cluster. And that would be one way of picking the points. Later on, we'll examine other ways of doing this much better. Now that we have clusters populated with these k points picked at random, here's how we're going to proceed. We're going to go through all the points in our data sets. And for each point, we're going to place it in the cluster to whose centroid it's closest. So we're going to find the cluster with the closest centroid to the data point, and then we're going to assign that data point to that cluster. Okay? And we're going to do this for each data point. Now, when we assign a whole bunch of new data points to a cluster, the centroid of the cluster might change because of all the new data points that have been added to the cluster. So we're going to update the locations of the centroids of each of the k clusters by taking into account the new data points that have been added to those clusters. Now, once we do this, we'll find that the centroids of the k clusters have moved, and now a point that was close to one cluster might be closer to another cluster. So we're going to go through and reassign all points to their closest centroid. And sometimes this moves points between the clusters. Now notice that we may have to do steps 2 and 3 again and again. And this is exactly what we're going to do. We're going to repeat steps 2 and 3 until convergence. And what we mean by convergence is that the k centroids don't move any further, and the points don't move any further across the centroids. At that point, we have a stable k-means clustering. So let's look at an example. So here's a set of points, and we're going to arbitrarily say that k is equal to 2. So we're looking to find 2 clusters in this data set. Now in round 1, I'm at random going to pick 2 points since k equal 2 and call those the centroids of the 2 clusters. Let's say I pick these 2 points, the point that I've highlighted with the in pink here and the point that I've highlighted in blue here as the 2 centroids. I pick these totally arbitrarily and at random. Now, what I'm going to do is I'm going to go through all the data points, and for each data point, I'm going to assign it to the centroid that it's closest to. So observe that this point, for example, here is close to the red cluster. So I'm going to assign it to the red cluster. Whereas this point here is closer to the blue cluster than to the red cluster. So I'm going to assign it to the blue cluster. And when I go through all the data points and do this, here's the clustering that I end up with. These 2 points here end up in the in the pink cluster here, and this set of points are closer to the blue point here, and so they end up in the blue cluster. So that's round 1 of k-means clustering. Now what I'm going to do now is, because I've created these 2 new clusters, I'm going to compute their new centroids. And when I compute the new centroids, the centroid of the pink cluster moves over a little bit to the left to this new position here, and the centroid of the blue cluster moves to that new position. Now, because I have new centroids, I'm going to go through, in round 2, I'm going to go through each data point again and assign it to its closest centroid. And when I do that, observe that point, for example, this point here is now closer to the pink cluster than it is to the blue cluster, and so it moves from the blue cluster to the pink cluster. Okay? And so we have this new clustering at the end of round 2. Now that we have the new clustering, I'm going to recompute the centroids once again. And when I recompute the centroids, the centroids migrate further. And because the centroids are migrated further, I have to recompute the assignment of points to the centroids again. And when I do that, these two points here then are closer to the pink cluster, so they move to the pink cluster, and we end up with the clustering shown here at the end of round 3. Okay. Now, as it turns out in this case, round 3 is the last round. At this point, the centroids and the points don't migrate any further, and we have a stable clustering. So what we have here is the clustering, the k-means clustering for k is equal to 2 for this data set. Observe that I started from a completely random assignment of centroids, and I actually migrated the centroids to where they finally ended up. Now, an important question here is how do we pick the right value of k? In the previous example, we arbitrarily picked k is equal to 2, and that actually turned out to be the right value for that data set, because you can see that there are roughly 2 different clusters of data points here. But in general, how do we know what the right value of k is up front so that we can pick the number of clusters up front? So since we don't know the right value of k, the obvious answer is to try different values of k and see what looks good. Now we have to decide what do we mean by what looks good. One obvious answer is to look at the average distance of points from the centroid as k increases, right? And let's look at an example to see what we mean here. So here's an example with a bunch of data points, and I've actually picked k is equal to 2. Because I picked k equal to 2, we have 2 clusters, and you can see that that's the centroid of the first cluster. And you can see there's a lot of points that are very far away from the centroid in this case, right? Now, if k is too small, as in this case, then there are going to be lots of points that are a large distance away from the centroid. So the average distance from the centroid is going to be fairly large. Now, I made k equal 3. And as it turns out, this is the right value for this data set. And you can see that the distances to the centroid shrink quite a lot. When I went from k equal 2 to k equal 3, that splits the top cluster into 2, and that shrinks the average value, the average distance to the centroid significantly, right? But if I increase k further, let's say I make k equal 4, and that splits that cluster further. Now, that does shrink the average distance of the centroid, but not as much as when we went from k equal 2 to k equal 3, right? So when we make k too large, it does decrease the average distance of the centroid, but not as much. Now, you can see this very clearly if I plot a graph. Right, if I plot a graph where the x-axis is k, the number of clusters, and the y-axis is the average distance to the centroid, you can see that as k increases, the average distance to the centroid keeps falling. But at some point, there's a knee in the curve, and the average distance to the centroid falls only very slowly. The obvious thing to do is to pick a value of k that's close to the knee of the curve, where you get a fairly low distance to the average distance to the centroid without too high a value of k. So in this case, the best value of k is the one that's shown in the picture. The final question we need to address with k-means clustering is the picking of the k initial point to initialize the k clusters. In the examples that we've seen so far, we picked the initial k points completely at random. Now, that worked out well in our example, but in general, it may not work out quite so well. We might, for example, pick k points that all happen to be in the same cluster, in which case the final clustering won't reflect the actual clustering of the data, right? Or we might pick points that are outliers that are not near any of the real clusters. So the final clustering depends on the initial k points that we pick, and so it's important that we pick the right k points to start the clustering from. The first approach to picking the initial k points is sampling. So remember, the data set is really large, and so we can't actually run a complicated algorithm like hierarchical clustering on it. But what we can do is to sample the data and take a smaller sample of the data. And then using the sample of the data, we can run another algorithm like hierarchical agglomerative clustering, which we covered in the last lecture. And we can run that algorithm until we obtain K clusters. And then we can pick a point from each of the K clusters. For example, we could pick the point that's closest to the centroid for each cluster. And we could call those our initial K centroids. Another approach is to not resort to another clustering algorithm, but to just pick a dispersed set of points, points that are as far away from each other in the data set as possible. So one approach to this is to first pick the first point entirely at random. Now, the second point we pick to be the point that's as far away from the first point as possible in the data set. The third point we pick to be the point that is as far away from both point 1 and point 2 as possible. In general, we pick, once we picked the first few points, we pick the next point to be the one whose minimum distance from the already selected points is as large as possible. And then we repeat this until we pick K points. So this ensures that the K points that we pick are as far apart or as dispersed as possible in the data set. And that gives us a better chance of finding the right clustering. Let's consider the complexity of K-means clustering. Now, in each round, we have to examine each input point exactly once. We have to find the closest centroid to that point and assign it to that centroid. Now, since there are n points and there are K centroids, right, we have to compute the distance of each point from each centroid. So the algorithm is order K times n for n points and K clusters. Now, each round is of complexity K times n. Now, this is actually not bad because when n is really large and K is fairly small, we have a linear algorithm in n. Each round is actually linear in n. But the real problem is that the number of rounds to convergence can be really, really large. There is actually no theoretical limit on the number of rounds for the algorithms to converge, and the number of rounds can be really, really large. So the algorithm could spend actually a really long time getting to convergence. So the question is, if the data set is really, really large, and we don't want to go through this large number of rounds, can we actually do something like K-means clustering in a single pass over the data? Because we have a really large data set, and we don't want to scan it multiple times. We're going to answer this question in the next segment.